So first of all, I'd like to thank the organizers for putting together this wonderful program and giving me the opportunity to talk. So yeah, I'll talk about work in progress with Francesco Benini and Eduardo Garcia Valdecasas from CISA. And it's about some entanglement measure, entanglement asymmetry, and symmetry or lack thereof in various systems. So I assume that most of you aren't familiar with what entanglement asymmetry is. So let me first just say what it is in words. Of course, since it's so informal, you should interrupt me at any moment and so on and so forth. Yeah, so let me just say in words what entanglement asymmetry is. So entanglement asymmetry is a particular entropic measure that faithfully captures symmetry break. And I'll go into much more detail later on its precise definition. But for now, just take this as a working definition and note the words entropic and faithfully, meaning that there will be some entropy involved, some entanglement entropy usually. And whenever there is symmetry breaking, this measure will show it. And in particular, it has some inputs and some outputs. So as an input, you give it your favorite quantum system that is more or less well-defined, by which I mean hopefully not quantum gravity, even though some of the thoughts and motivations behind that, at least for me, are to be able to think about quantum gravity eventually, but some well-defined quantum system, some lattice model, many-body system, some QFT, something. Optionally, a subsystem some state, which could be mixed or pure, a density matrix at all, and some group, G, which I'll regard as a symmetry group of that system. But in general, this is what you need. And the output is a number, delta S, I'll call it, that is between 0 and the dimension of the Hilbert space, and log of the dimension of the Hilbert space of that quantum system that you have. Of course, if that's a QFT, that could go to infinity, but it's not going to be a UV divergence. It's usually going to be some IR divergence. All right. Of course, oftentimes your system depends on additional parameters, lambda. So this will give some function of these parameters, lambda, that will be bounded by these two numbers. So with that, let me just motivate why one wants to think about this quantity. Oh, that's the shadow you were telling me about. Okay. And that's, first of all, okay, there are two pieces of motivation that I need to clarify. First of all, why entropic measures? And secondly, why this one? Okay, the first answer is just going to rely on a survey of some important examples where entropic considerations give us useful information. And for instance, in 2D CFTs, we all know the Calabrese-Cardi formula. That's the entanglement entropy on an interval behaves like C over 3 log of the length of the interval over some short distance cutoff. And since there's this program about boundaries and defects and so on, in 2D BCFT, you also have the Affleck-Ludwig terms. Which basically, the point I'm trying to make with that is that this characterizes universal information of the underlying theories. And that's the only thing we need to calculate that. Secondly, another important example, again, that fits in with the theme of this program. Try to switch the boards. This is going to go terribly. Not that bad. Okay. Is classic. Sorry? Yes.
Yes, I think it's already appeared in the paper by wheelchair collapse.
That's true. That's true. It's just known as the Calabrese-Cardi formula, but indeed there was in this paper before.
And maybe even in Sredniki.
That I don't know.
He definitely has two-dimensional result, maybe without C.
Maybe what?
Without central.
I see. I see. Okay. Thank you. Yeah. Okay. So the second example I wanted to outline is in 3D topological order, and by 3D because I'm trained as a high-energy physicist, I mean 2+1D. Topological order, or topologically ordered phases of matter, where if you calculate, say, if you take a spatial slice, say this is your spatial slice, time goes up. This is some slice at sigma t equals 0. And then you wish to calculate entanglement in some subregion, A. Then you realize that there's some contribution from modes that live close to the edge of A. And this contribution goes, roughly speaking, as L over epsilon, where L is the length of the boundary of A. So L is length of the A, minus some constant correction term, some finite constant correction term, which is known as the topological entanglement entropy, and is something finite, universal. Is this color all right? Something finite, universal, and is characterized by the total quantum dimension of the anyons that are inside this topological order. So essentially, it captures the effective anionic degrees of freedom there, and it's some universal piece. And there are more important examples. For instance, even though I said I will not discuss it, in quantum gravity or in gravity in general, you have the Bekenstein-Hawking entropy, whereby the entropy of a black hole is captured by the area, and holographic, and it leads essentially to the whole field of holography and ideas about that, and obviously many more recent progress, much more recent progress, as well as a lot of monotonicity theorems about the renormalization. For instance, the C theorem in 1+1D can be recast as a question about entanglement entropy. You can write a function that is something like that, where R is, maybe I should call it L because I called it L before. Something like that. And then this is monotonically decreasing, and it shows that the IR degrees of freedom are strictly lower, fewer than the UV degrees of freedom, and further generalizations. By the way, sorry, since this is a Blackboard talk, I will be very bad with references because I can't write all the references, but this was Cassini and Huerta in 2004. And generalizations, but all in all, the general feature is that even if we're given access to some finite portion of space-time, in all these examples is finite portion of space, but recently there is some ideas of weak rotating part of it into time. But in general, even given even given access to a finite portion of space-time, we can still take away universal features of the underlying theory. We can still write down universal features by considering entropic quantities. So okay, the second piece of motivation is why this particular one? We all know we have order parameters, so why care? But these order parameters have some difficulties. So they signal spontaneous symmetry breaking, but it's not always easy to find them. For instance, we find them case by case, or in higher form symmetries, these are extended objects. For example, in a higher form symmetry breaking scenario, by SB I will denote symmetry breaking, and SSB either spontaneous symmetry breaking or soft symmetry breaking. It's usually going to be spontaneous. Then you have extended objects as order parameters. So here is a Wilson loop, for instance, that exhibits either an area law or a perimeter law, and signals when the symmetry is broken or unbroken. And there is a sort of attempt at a Landau paradigm for this sort of symmetry breaking, but due to Nabil Iqbal and John McGreevy. But it's very difficult to work with. It involves sort of mean string field theory actions, if you will. And even more difficult is the case of categorical symmetries or non-invertible symmetries. Where it's again very difficult to find order parameters for these things. They sort of exist. There is a Landau paradigm program for this as well by Bardwaj, Bottini, Payer, and Stefanameki from Oxford. But still it's very difficult to work with. So besides, since even here we're giving up locality, so the good thing about the Landau paradigm was that the order parameters were local and we could write a local mean field theory to capture them. So since we're giving up locality to capture spontaneous symmetry breaking of high form symmetries, why not give it up completely and just consider some entropy and see what we get? Besides, another benefit to using this measure, as I will try to convince you later, is that entanglement asymmetry is, so by EA, I will denote entanglement asymmetry. Is better suited to study subsystems or subregions and also for out of equilibrium questions, meaning I can prepare my state, then I can quench it to a Hamiltonian and let it evolve and study what happens, which I can't do so easily with the Landau paradigm. So with that, hopefully I've convinced you a little bit that this is an interesting subject to study, and I will go on and define it properly, unless you have any questions in the meantime. Potentially. It has some benefits. Yeah. Order parameters are better for other reasons. For instance, you can just use mean field theory and you know what to do with it. This is difficult because you need to know a state. You need to know an exact state of your quantum system, which is not always very easy to construct. But yeah, it has these sort of benefits that I mentioned. Yeah. Yeah. For instance, a coupling constant. Your system could have a coupling constant, and then everything that follows that you extract out of it depends on that. Yeah, and so does the asymmetry.
So motivation you presented was for higher form and other categorical symmetries. Are there motivations even for ordinary symmetries?
Yeah, subregions and out of equilibrium questions.
Okay.
It's enough. It's, well, I'm saying entropic measures, right? Yeah, but how can you capture symmetry breaking with entanglement entropy alone? You capture some of it. You don't capture everything, really. The dependence on how the subregion is embedded inside your region. Gamma only knows about the... Yes. Yeah, but maybe you have access only to that. For instance, again, my motivation could be, yeah. Maybe it's not, I don't know, big. Asymmetry captures interesting features, as you'll see in a second.
Quantity though, it's UV finite?
Yes. So in QFT, it's UV finite so long as the symmetry breaking is either spontaneous or soft, only in the infrared, basically. But maybe I will show you in a bit how UV divergences essentially cancel. When you see the definition, I will comment on that. That's right. Yeah, yeah. That's a good objection. Yeah. Thanks. All right. So let me then define it properly. So let's take some quantum state and let's pretend that, for the sake of illustration, that I have some spin chain. I have a bunch of spins living in this chain. And this is my state. And I create, again, for the sake of illustration, here this pure density matrix psi psi. And then I would like to reduce the state to a subsystem. Say, for instance, I'm interested in only these three spins, and the rest I call the subsystem I don't care about. Oops. Okay. So in this case, the Hilbert space factorizes into Hilbert space on A and one on B. I know that in quantum field theory, this is not quite true. If you break it into a subsystem, you need to be careful with how you factorize the Hilbert space, but I will be careful when I go to the case of QFT. So let's assume that it does factorize. And now have a reduced density matrix only on A that is given by the partial trace of this pure density matrix. And let's say, moreover, that I have some conserved charge, some symmetry, that is generated, that breaks up between the two subregions. So I have one contribution only on A that acts trivially on the rest, and a contribution that acts trivially on A and only on B. So then, on the Hilbert space, the charges, on say this reduced Hilbert space, the charges act by their exponentials. So if you imagine the case of a U1 symmetry here, they act by e to the I alpha q A, where alpha is some angle. Otherwise, it's labeled by a group element instead. So the question is, how do I measure if this quantity breaks the symmetry? And furthermore, does it make sense to ask how much does it break it? Yeah, another perhaps motivation is that this measure is quantitative rather than qualitative. It doesn't just answer yes, no. It answers yes, a lot, or yes, a little, or no. Okay, good. So how do I ask if it breaks the symmetry and how much? So generally, this density matrix that I have and I'll now be just talking about the reduced density matrix. So this density matrix that I have, I can write it as such. It's a matrix. And say it has some block with charge Q1, another one with charge Q2, and so on. But it may also have off-diagonal elements. It may have an element here, here, and whatever. So if that's the case, then you can show that it does not commute with a charge. So in some sense, you've already answered the question whether it breaks the symmetry or not. If this is true, if it does not commute with a charge, then it does break the symmetry. But the question is, again, how much? So I need to compare it with a density matrix that I've constructed such that it preserves the symmetry. So let me construct that density matrix. It's very easy. I'll call it rho symmetrized. And it's just essentially killing off all the off-diagonal terms. Okay, killing off all the off-diagonal terms. And how do I construct that? I basically say, let me take a projector onto the subspace of charge Qi, project my density matrix like that, and then sum over all possible i's, by which here is a direct sum, really. And if you want, I can Fourier transform these projectors. Can you see for it so low there? You can't. Okay, so how can I rewrite this projector? Actually, maybe I can even just do that. I can Fourier transform it. And here I'm just writing it in the case of a U1 symmetry. Into something like this. So I take my symmetry generators and I act on my density matrix, and then I average over the group, basically. It's a very stupid construction, but it works fine. Yeah. Modular symmetry? No, why? On site, you mean? Is that what you meant, or? Yes, yes. Yes, yes, this is what I wrote here. So the charge acts as identity, so the charge splits into a part that acts only on Hilbert space A and identity on B, and one that does the opposite thing. You need boundary conditions to ensure that that's the case in quantum field theory if you wish. But yeah, that's the standard assumption. Do you have a question? That's the standard case, I think. For instance, just let's say in the XY chain that you rotate the angle of each spin. Then if you break up your chain into A and B, you can restrict to rotating spins only within A. Right, right. Is that so? Okay, I was not aware. I see. I do know that there's some work on entanglement asymmetry for integrable systems, So I suppose that they've overcome this problem, yeah. But thanks, yeah. Okay, very good. So now let's define this quantity that does the trick. And essentially, Eric's intuition that it's just an entanglement entropy, it's almost spot on, but it's just a difference of entanglement entropy. So you take, and I always get the sign wrong. You get, okay. So you take the entanglement entropy of the symmetrized density matrix, and you subtract the original entanglement entropy, or written down explicitly, did I mess it up? I think no, it's fine. Yes, and then you can see that because I had written it as in terms of a projector, so I had written rho AS as a sum over projectors, you can really recast that as a relative entropy between rho A and rho AS. Essentially, the point being that I can factor rho A here. I can write it like this, basically. Well, it is, but it just so happens that because this is a projector, it can be recast as a relative entropy. Basically, you see that since this is a projector and this is, so these are projected and these are projected, it suffices to only have one of the two projected, the inner one, which is a non-trivial operator. All right. And so, since this is a relative entropy, first of all, this answers your question, why do UV divergences cancel? Because UV divergences here would be the same as here, or rather, relative entropies are better behaved than entanglement entropies, usually. And secondly, we can deduce the following, that this is a quantity that is positive, that is bounded from below 0. And it is 0 if and only if rho A is equal to rho AS. So that's the quantity. It's as simple as that. And then we'll see how far it gets us. Yeah.
Thinking only of zero-form symmetries, or is this all true for?
The main idea of this project is to extend it to higher form symmetries. So I will extend it in a second. Yes.
And is this thing the symmetry resolved?
No. Good. Very good question. So yes. So the symmetry resolved would be to calculate the entanglement entropy of this quantity. So you have a projector on the space Qi. So let me call that rho Qi. So this, the entanglement entropy of this quantity, is the symmetry resolved. In my case, I had a sum over all possible charges. So here would be one of the blocks, basically. Now I have all of the blocks, and I compare them with the unsymmetrized density matrix.
At this stage, can you tell the difference between explicit?
Very good question. No, I can't at this stage. I need to make sure that I have a ground state to say that. In general, yes. In the general case, we'll have various entries filled in. If the symmetry is unbroken. If the symmetry is unbroken, right? Yes. Yes. But it may be broken. So I did find a way to write it like that. I did symmetrize it. And then I say, okay, let me compare it. Let me, I did this step. And before declaring that this captures the same thing as before, let me first compare it to make sure. And I compare it and I find something non-zero. Sorry? Any state. Any state. Choose your favorite state. Yes. Okay. You'll find it, you'll see it in a second. I will do applications. But it could be zero or it could be non-zero. And it's non-zero when there is spontaneous symmetry breaking. You'll see it in a second. I'll go there.
Is it some kind of canonical state here? Can you say anything about it with the symmetry?
You want it to be thermal, you mean? Is that what you mean?
Yeah, some kind of universal thing. No charged operators have VEVs, and you haven't introduced terminal Hamiltonian to break the symmetry.
So first of all, the Hamiltonian does not matter for this case. You just bring a state. You just write down a state. Secondly, indeed, if that was your state, there are no operators with VEV, with non-zero VEV. But in that state, there may be, right?
My question is, like, is this
Yes. Given a state A, I can uniquely write it like that, right? I can just project on any is some sort of a canonical procedure.
all you know that it's symmetric?
Yeah.
Could be any symmetric state.
Yeah, I guess. Sorry, maybe you're asking what are the entries within this block diagonal within these blocks, right? Maybe that's what you're asking. And indeed, I suppose I can reshuffle the entries in here, so that's not unique in that sense. But so long as it's block diagonal, it's fine.
Say, like, pick any symmetric state.
Yes, 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 yes. But the canonical way to construct it is by acting with these operators. Then for non-invertible symmetries is more tricky. I will not go into that, but there were 2 papers very recently that did that case. Yeah.
Will you get different answers depending on the like, for example, if you just had ideal model,
Yeah.
and you considered all up spins or all down spins, would you get different answers?
No.
Okay.
In
so
that case, you get the same. Yeah.
I see.
Yeah.
If you just consider any state, how do you then relate the symmetry breaking of that state? If you like not using the ground state, how do you relate it to symmetry breaking of the phase? I mean, if it's just a
No. Sorry. Good. The result in that case would be, you would ask me, does that state, I give you my state, does that state break the symmetry? I would say, yes, that state breaks the symmetry. Then you'd ask me, is my system in a spontaneously symmetry broken phase? I'd say, I don't know, you didn't give me a ground state. Then if you gave me ground state, I could answer the first question and then the second question. Yeah. All right. By the way, yeah, some historical remarks about this quantity. It's the 3rd time it's been reinvented. So first it was invented in quantum information by these people, Vaccaro, Anselmi, Weismann, and Jacobs in 2005, already 20 years ago. Then it was reinvented in a sort of different disguise by Cassini, Huerta, Magan, and Pontello between 19 and 20 under the moniker entropic order parameters. Here it was just called asymmetry, or relative entropy of asymmetry. Anyways, and then it was reinvented by, sorry, I forgot to really mention when did this arise. I'm terrible at that. It was by Ares, Calabrese, and Murciano a few years ago in 2022. All right. So it has been applied. Oh, sorry. What do you mean a lot?
Like, for example, is there like an area law or
It does not depend. It does not have area laws and stuff like that. More particularly, it does not depend on any UV regularization you choose to regulate your subregion. So in that sense, it only depends on rough characteristics of the subregion. But yeah, this is not a very precise answer with you. All right. Yeah, so there are many applications of this concept already. As I mentioned, indeed, in integrable systems and in spin chains, matrix product states. I will not give references now because there are a lot, but you can ask me later and I can tell you where to look at in CFTs and recently in non-invertible symmetries. And there have been some mentions about connections to holography. Maybe one funny observation about this thing. I realize I'm doing very badly on time. Okay, is that there is a sort of funny effect that they called quantum Pemba effect in Pemba. So quantum Pemba effect. Whereby if you say you calculate your entanglement asymmetry and then you quench your system to some Hamiltonian, so and you let it evolve in time, and you have some states that depend on time, and I start with a state. So as I told you, the higher this number, the more the symmetry is broken. I start here somewhere. I have another state that breaks it less. What ends up happening is that this state relaxes faster than the other state, than the state with less symmetry breaking. And that's sort of analogous to a classical effect observed by Mpemba, a Tanzanian high school student, about freezing ice cream. It's a funny story. But yeah, so that's an effect, and sometimes it happens, sometimes it doesn't. There is a reason behind that for integrable systems that don't ask me about, because I don't know exactly. And it's unclear why it happens in some other cases. Yeah.
You're starting with some state that breaks symmetry, and you're quenching it with a Hamiltonian that
preserves it. Yes, yes, yes. Precisely.
For integrable systems, this effect is not.
It does, but the origin is known. Why it happens? It's known why it happens. I'm not sure. I don't know for which ones it does.
Sometimes works, but we don't know when.
That I don't know when.
Okay.
People that worked on it do. Okay, so wow, I'm doing so badly. I haven't even talked about entanglement asymmetry, but for high from symmetries. Okay, I'll have to rush a bit. Okay, anyways, so this was a very easy definition, but let me rewrite it in a slightly more difficult way that will end up generalizing very naturally to higher form symmetries. And let me first choose to not choose a subregion. So let me first suppose that I have some, now I'm moving on to QFT side, I have a QFT quantized on some Cauchy slice sigma. It's a d-dimensional QFT. So it's quantized on some d-1 dimensional Cauchy slice. And I want to consider operators that act on this Cauchy slice, on this entire Cauchy slice. So let me represent the Cauchy slice by a circle. Let's say that time was like this. And now I have operators that are labeled by some d-1 dimensional cycle, the Cauchy slice here, are acting on this space. So And I will also, for simplicity, assume that my symmetry group G is abelian in this case, because I want to generalize to higher form symmetries in a second, and for that case, I only need abelian groups. So for all that matters, you can think of it as a U1. So these symmetry operators are labeled by some angle and some d-1 cycle. So this is an element of the d-1 homology group of sigma, and this is just some angle. But equivalently, I can label these by some group valued homology class, d-1 homology class. Essentially just by absorbing this angle inside the homology class. Yep. It becomes trivial, yes. All right. And that's, for instance, for continuous symmetries, you can see it by the conservation of current, if you want. But this operator would be something like this. So then if this was a boundary, you can pull it in and conservation of current, see that it vanishes. It's trivial. Okay. And for discrete symmetries, you just postulate it essentially. Okay, which is just isomorphic to the group itself, to the number of connected components of sigma. Which, as any reasonable human being, I will assume that sigma is connected. And it generalizes easily. Okay, so then starting with this state, this rho A that I had, which here I don't have an A, so I'll just call it rho. I can act left and right with this UA. It's easier if I write it like that. UA. And to symmetrize, I have to integrate over this group that I'm just erasing. So I have to integrate over this, and this will give me the symmetrized state. You can see that you can show that it's exactly equivalent to the previous definition I had, and when the group is discrete, this reduces to a sum. When it's continuous, this is just the push forward of the hard measure of the group, and so on. So it's the same definition as I had before. Now, to go on to acting on subsystems, I need to further assume, so let's say now that I want to act on half this space. So I don't want this. And I only want to act on this thing that remains that I'm going to call A. So now I would like to assume that my operators here can terminate on the boundary of A, and end on the boundary of A. So in that case, they would be labeled not by a homology class of A, but by a relative homology class of A relative to its boundary, again, valued in the group. And that's the only thing I need to change to consider subregions, basically. And again, you can show that this is the same as G, this time to the number of connected components of A. So perfect, that works fabulously for what I want. And now it's very, very easy to generalize to higher form symmetries, because the only thing that changes is that they're not labeled by a d-1 cycle, but say if I had a p-form symmetry, they're labeled by a d-p-1 cycle. So the only thing I need to do is amend this number here to d-p-1. And that's essentially how easily it works for high form symmetries. And you define it in the same way that, is it written here? Yes. Or no? No, it wasn't. It was written here behind. But you define it in the same way. You take the difference of the entanglement entropies of the symmetrized and the unsymmetrized state. And again, you can show that delta S is positive and is 0 if and only if rho A is rho A symmetrized. Any questions so far? Yeah. I repeat the same answer. I will show you in a bit. Oh, okay. Okay, then I have to probably rush through some things. But okay, it's not always 0. Yes. But I also have a lot of things to say still. No. In that case, I think it is 0. But if you take, say, a free compact scalar, it's not in, I don't know, 3 dimensions. Yeah, 3-dimensional compact scalar. A 2-dimensional compact scalar is 0. A 3-dimensional one is not, because it is then the Goldstone mode of the breaking of the symmetry. I'm really spoiling the rest of my talk, but since I'm running late. Anyways, okay, I was planning to talk a bit about how to compute it with path integral methods. I might do that quickly and then skip the topological order and ask you to ask me later. But in any case, so the point is that oftentimes I can write my states, and I have a QFT set up now. So I can write states on sigma as prepared by some path integral, some Euclidean path integral, perhaps with some insertions on some manifold whose boundary is sigma. That's not always the case. That's not the most general case, but that's a wide class of states. And in some cases, for instance, CFTs or free theories, it is the most general case. And then the density matrix associated with that state, you can then view it by drawing this picture, essentially. Okay. And now I want to play the same game as I played before. I want to break up sigma into A and its complement. I want to break up sigma like so. So to do that, I need to define it in some way that the Hilbert space factorizes between A and its complement, which is not always clear how to do it. But one way that works, that was elucidated a lot by a work in Ohmori and Tachikawa from 2015, is to say that I have a buffer region between A and its complement, on which I essentially create an artificial boundary on which I impose boundary conditions for all my operators. And this schematically can be viewed as the following Euclidean path integral. I start with sigma, and I end up in this geometry. And then I need to impose boundary conditions on the boundaries of this brick wall regulating surface. So after doing that, yeah, sorry.
Are you schematically drawing a 1+1D system?
Yes.
And the 1+1D
In the higher
system lives on the boundary of your, like it's not a 2D surface.
This is a 2D thing. This is a 1+1 theory that lives here. This is a one-dimensional Cauchy slice, a circle, and time.
Yeah.
Euclidean time. Yes, you're right. Importantly. Okay. So after doing that, I can play this game with my density matrix and define the reduced density matrix on A by essentially gluing everything that isn't A or its buffer region. So with that, I end up with a geometry that looks schematically like that. And of course, this is only I'm only drawing the topology part because the geometry part is complicated, but it looks roughly like this sort of weird Pac-Man sort of figure. And here is where I glued the rest, my region. Here are my insertions, which I will, in order not to draw it like that, I will open it and write it like so. And then having done so these are, again, schematically all my insertions, I just bundle them into one. After having done so, I now want to define the symmetrized density matrix, which means I need to first see how to act with symmetry operators on this state. And that now I can do. By just taking my symmetry operators, so let's say that this is labeled by, this is U alpha. And let's give them an orientation. So now these act directly here, right? So I should have actually drawn it exactly on top. But you can see that I can deform them slightly. So let's say I don't deform the endpoint here. I can deform them like this, for instance, because they're topological. And then I can deform them completely to bring them next to one another. Let me redraw it so that it's easier to visualize. So I had my insertion, and I can completely deform the operators such that they surround the insertion, but I've got left their action on the boundary. No. Okay. So now I need to discuss boundary conditions here. Is this 0 or non-zero? There are two, so these are the two choices. One is that it's 0. These are symmetric boundary conditions. In the sense, sorry, not 0. Let's say that my boundary condition before was B, and I will denote it by a state, as oftentimes people do. So then one option is that U acting on B gives B. And the other option is that U acting on B gives a different boundary condition that I'll denote alpha times B. So the first ones exist only when the symmetry is not anomalous. They're equivalent essentially to gauging the symmetry. And the second ones exist always. Right, so keep that in mind. There are some comments that even if you don't have available a symmetric boundary condition, you can still take a classical mixture of density matrices with different boundary conditions such that you isolate the contribution of the boundary and you remove it. And the contribution of the boundary was studied in detail by two groups, by Kusuki, Murciano, Guri, and Pal, and Fossati, Rylands, and Calabrese last year. And yeah. Anyways, I will not go into detail with about that. I will assume symmetric boundary conditions for now. Actually, no. Yes, let me assume it to have it clearer. Right, so now to work with entanglement asymmetry, it's oftentimes useful to consider some close cousins of entanglement asymmetry that are obtained by the replica trick, the Regni entanglement asymmetries, the Regni asymmetries. So these are defined as so. Yeah. Yes.
You need to insert an operator to have non-trigger.
Yes. If you don't have an operator, or if you don't have any sort of non-trivial feature in the bulk, the operators just go in and kill each other and go out. They don't have, the result is trivial in that case.
So you're considering excited states, not the ground state.
No, it could become the ground state. The ground state is not always prepared by the identity operator. In CFTs it is. But say Again, in the 3D compact scalar, it's not. Again, this was just the topology part of it. For the, you need to have in mind what the geometry behind it is. And in my example, if I manage to get there, I will be precise with it. Anyway, right, so you consider these close cousins, and basically you take this density matrix, the symmetrized density matrix that I just probably erased, that was here, and you replicate it several times until you get to a picture that looks like this. So when you take the trace, you will essentially glue the last part. So, for instance, this was my density matrix. So I glue this part to get. This is the double density matrix. And then I glue several copies of it, and then the last step I will close it down again. Sorry, this drawing is really bad, but I'll draw a better one here. Anyways, once you play this whole game and replicate it several times, you end up with a picture that looks something like this. And you had these operators here. And then you surround them by the various operators that you had. Alpha 1, alpha 2, alpha 3, alpha 4, let's say. And you integrate over all these alpha i's. So this is the picture of the numerator. This is calculating the trace of the reduced density matrix, the trace of the replicated reduced density matrix. And then the denominator is just essentially this. Okay. Other questions? Okay, good. So if not, I'll go to the examples, to the applications. So one quick application I had was about topological order, but sorry. There. Yes, of course. Sorry, I forgot to draw them. There. Okay, so I had a very mundane observation about topological order that in view of time, I think I will skip. But you can ask me later. Basically, it's calculating this quantity for spontaneous symmetry breaking of discrete symmetries and for discrete gauge theories. And then I will go to the main example, the main application that I wanted to discuss, which is about continuous symmetries, so continuous p-form symmetries, and their symmetry breaking or not. So let me go to my favorite system that has a U1 p-form symmetry. So I want some U1 p-form symmetry. I'll denote it like that. So let me go to my favorite example, which is, as always, Maxwell theory, or in this case, Maxwell theory with p-form gauge fields. So its action is like this. I had to include some arbitrary energy scale, and this delta is just d minus 2p minus 2. In which case, when p is when d is 2p plus 2, this theory becomes conformal. You don't have to becomes scale invariant. You don't have to have a scale to write it down, and in fact conformal. In other cases, it is scale invariant but not conformally invariant. So this thing has this theory has a U1 p-form symmetry whose conserved charge is exactly the integral of star f over some d minus p minus 1 closed cycle. And it also has a dual, so this is usually dubbed electric symmetry, and it has a dual magnetic symmetry, which is a d minus p minus 2 form symmetry, and the two have a mixed anomaly, and very nice things come from that, but I will not discuss the dual symmetry at all in this case. And I want to just calculate the entanglement asymmetry and finally answer Eric's question if I'm on time. Okay. So let me warm up by by considering no subsystem, just quantizing this theory, some Cauchy slice that I will take to be some sphere, some p sphere with radius r, times some d minus p minus 1 sphere with radius capital R. And why do I consider this thing? Well, so first I want to have some d minus p minus 1 cycle such that I consider this entanglement asymmetry in the definition that I gave. And then the rest could be essentially whatever. It's just that a p sphere causes the least amount of trouble, because for any dimensions that aren't 2p plus 1, it does not give rise to other cycles. So I will actually consider that. Everything generalizes if d is 2p plus 1. It's just more complicated to write down. Okay. So let me just write down the states here. What is my Hilbert space? It's a free theory. I can solve it exactly. So the states, I can essentially classify them as such. I have some states that are called K, which are uniquely specified by the fact that they have a fixed charge K, meaning the action of these operators is e to the I alpha k on these guys. And the Hamiltonian acts, so, and they're energy eigenstates, whose energy measured in units of R is exactly this. And perhaps I'll actually consider lambda equals 1 because I can absorb it inside mu. So yeah. So their energy is this. So these are energy eigenstates with a fixed charge. And then on top of these guys, I can act with your usual QFT 101 creation operators. Even though here they're in compact space, so the momenta are, the quasi-momenta are quantized. And so on. So these are all my states. So, and these are labeled by an integer. So the charges are integers. That follows from flux quantization, essentially, if you want. Okay. So sigma is the entire Cauchy slice in this case. This is a warm-up example. Okay. Perfect. So now I will eventually want to end up on ground states. So it's clear that all these states can never be ground states. They just raise the energy by some fixed amount. So I want to consider these states, some collection of these states as my state to begin with. And it's clear to see that I can write down a state that breaks the symmetry maximally, in the sense that it breaks it as much as it can, which will be labeled by some parameter theta, and is nothing but the Fourier transform of these states k. So you see that when you act with these operators on the states theta, what you get out is theta plus alpha. So essentially, if these theta were ground states, this would span the moduli space of vacuum, which is a circle. But this theta, here in finite space, don't have a fixed energy. They're just some combination of these states with finite energy, but they don't have finite energy. So I want to eventually be able to go to the ground state. So in order to do that, I'll consider the following density matrix, which is that I will take as a density matrix the obvious one, theta, theta, but I will then act on it with the Hamiltonian, so with some temperature beta. So I will perform some Euclidean time evolution, temperature beta or Euclidean time beta. And I will consider this as my state, which at the limit of beta going to infinity, it will have the effect of projecting down to the ground state. Because all states with non-zero energy will be projected out, will have zero weight in the sum of states. And then I want to calculate the asymmetry for this sort of state. And what is that? So I showed you how to compute it with path integrals, or in this case, I can just compute it with the definition. I don't have to do a path integral. I can just act with my operators left and right. And so then the Rényi asymmetries in this case are just given by this formula. So where this function that I defined, it's not really a partition function, although it's very closely related to it, is just a theta function, essentially, a Jacobi theta function. Is e to the minus, let me get this right, minus beta over r, mu small r to the p. Sorry. Yes. So it's this function. Okay. Very good. So this probably doesn't tell you much. You can't do it in your head to see how it goes. Perhaps some of you can. But let me plot it for you. So, and let me make two plots. One is for fixed mu r. So for the time being, I'm going to set this thing to 1 because it will not play a role, so that I don't have to carry it around. This is fixed forever to 1, and you can reinstate it later. But this will always be some finite sphere. I want to play with the other one. So first, let me fix this combination and plot it against Euclidean time over R. This is the other dimensionless combination that I can write down. And I'll plot it for various p. So I had a p-form symmetry. And let me save, sorry, I do not need to plot for various p. It's the same for all p here. OK, so for any random d and p here, the plot looks a bit like this. So what does this tell us? On the left side of the plot, so when beta over r is very small, this goes like 1/2 log beta over r. So what does this tell us? This blows up with when beta is very small. Is the color completely illegible? I guess so. Sorry. Oh, okay. It's log beta over r. So what is this saying? It's saying that the symmetry is broken a lot. There's a dense number of states. There are many states that break the symmetry. But of course, none of them is a ground state. All of them are, have no fixed energy. On the other side, when beta is very large, it has projected to the ground state, and the asymmetry is 0, which says that there is a unique ground state which preserves the symmetry at finite volume. So now let me give you the other plot. The other plot will be for fixed temperature. Yes? No, sorry. I can normalize it. This e to the minus beta h plays two roles. One is the one I told you that projects to the ground state, and the other one is it makes rho normalizable. Otherwise, it was delta function normalizable. And then here it's going to be some theta function like this. In some sense, this is, roughly speaking, trace rho. So I can divide by it.
It's not just a reflection that trace of your right
No.
row is getting smaller.
Yes, no. Thanks for the question. So OK, let me now fix the temperature and plot it as a function of essentially spatial volume. So I want to eventually consider an infinite volume limit to probe whether or not I have spontaneous symmetry breaking. OK, and here I'll need to plot for several values of p, because the plot changes. And let me fix d equals 4 just to have a lot of p to play with. OK, so for p equals 0, it goes roughly like this. Starts at 0, and then it grows like that. And the behavior is 1/2 log mu rho, in this case to the 2, in this case squared. Then for p equals 1, it again starts as 0. It starts at 0, it grows, but it goes, it's less steep. The behavior is just 1/2 log mu rho. You might guess it that when p is 2, so this is p equals 1. Sorry. P equals 0 here. P equals 1 here. You may guess that when p equals 2, this is just a straight line, a constant. And when p equals 3, it has the opposite behavior. It goes like this. This was supposed to go basically like this. When p equals 3. So what does this say? Yes. I think this is just an artifact of where all these things become 1, basically. OK, so it's not super clear what this says now, but let me consider a combination of these two limits, basically. So let me say that the physical limit that I want to consider is first, take the volume to infinity. So consider an infinite volume limit. And then, and only then, consider a low temperature limit. This goes to infinity. So essentially a combination of the behavior here and that one here. So what this does is it pushes down this plot such that this value becomes 0, and also this curve ends up becoming 0 as well. So in that limit, you have the following behavior of the entanglement asymmetry of that region. And wow, I'm doing well on time. Okay. So you see that it goes like log. So this is at mu r much larger than 1. It goes like log mu r to the d minus p minus 2 when d is greater than p plus 2. P minus 2, sorry. When d is greater than p plus 2. And it's 0 when d is smaller than p plus 2. So what is this? This is basically an entropic version of the Mermin-Wagner-Coleman theorem. It tells you that, so this limit guarantees that first I am at infinite volume, and then I project down to the ground state. So I only consider ground states. So it tells me that for dimensions p great, and let me temporarily fix p to 0 just to go back to the usual Mermin-Wagner-Coleman theorem. So when p is 0, it tells me that when d is greater than 2, this symmetry is broken spontaneously. This U1 symmetry in this theory that I considered is broken spontaneously. And this theory is exactly the Goldstone theory for the effective theory of Goldstones for this spontaneously broken symmetry. And the fact that it blows up is telling you that that is a continuous symmetry. If it was a discrete symmetry, this would have been the size of the discrete group that was broken. So in some sense, this is the size of U1, if you want. OK. And then when d is smaller than or equal to 2, the symmetry is necessarily preserved on the ground state. And so this is an extension to p-form symmetries, which is also known in the literature. So for p-form symmetries, it was proven by, well, it was first shown by Gayota, Kapust, and Seiberg and Willett in the original paper, Apart from Symmetries, and then further elaborated by Lake in 2018. And that's an entropic version of that. Yes. What? Yes. Okay. It's just nomenclature. It's entropy. I agree that the nomenclature shouldn't be entanglement asymmetry in this case. In fact, we're considering calling it state asymmetry, but then it's like, why introduce another new name, whatever? So, in any case, it has this name, delta S, call it as you may will, entropy, entanglement asymmetry, symmetrized entanglement entropy, captures the spontaneous symmetry breaking in this theory, and it shows that this symmetry is broken in dimensions greater than p plus 2, and is not in dimensions smaller than p plus 2. And let me, I have very, very few minutes, yeah.
Some people had conjectured that the entanglement pick up a long-term coefficient would be the number of Goldstone bosons.
Oh, actually, that turns out to be true because for non-abelian symmetries, say if you break to G mod K, if you mod H, if you had a symmetry group G and you break to G mod H, well, you break to H, sorry, then the coefficient in front, so here it would be only p equals 0. So for non-abelian, yeah, it would be dim of the Lie algebra G minus dim of the Lie algebra H over 2 in front, the log. So indeed, where was this conjecture at? Okay, thank you. Yes, I would be very interested. Okay, very interesting. That's very interesting. Nice. Okay, good. So that's one result. And then in the last, I don't know, 7 minutes or so that I have, I want to sketch a version of that when I don't have access to my entire region. So now let me take a subregion, and I'll show you that it's actually more interesting if you don't have access to the entire region. So let me consider the spatial slice to be more or less as before, but just in this case, I don't need both of them to be compact. So I consider my spatial slice sigma to be r d minus p minus 1 times some small sphere here that sits and does nothing over each point, so SP. And now I consider a subregion A that is basically a little ball of dimension d minus p minus 1 of radius capital R, as before, times this little sphere that comes here and annoys nobody. And I can play this game that I told you before. I have to be careful with exactly what the geometry is. So if I wanted to compute this replicated density matrix, I would now have to consider a path integral on n copies of that. So basically, sorry. I would have the trace of rho A to the n to be the partition function on an n-fold cover of R d minus p minus 1 with branch locus a d minus p minus 2 sphere of radius R times this little guy that does nothing. So this would be the trace of rho reduced to the n, which eventually you can carry out the computation. So that the trace of the symmetrized version of that is a very similar computation, but you now need to consider operators acting on each of the punctures. Maybe I'll say something more. Topologically, this can be viewed as d minus p minus 1 sphere minus n points, so it has n punctures, times these spheres that do nothing. and the n punctures are here. And then the trace of rho a to the n is just this. The trace of rho n symmetrized to the n, you need to have these operators encircling all these boundaries, and then integrate over the alpha I. And let me just jump straight to the conclusion, because it's a long computation that I don't want to show you. I can, if you want, afterwards. But what turns out to be the case is that delta Sn is captured by a very similar formula as I had before. So it's captured by this. So now I have a vector of integers. So the n minus 1 is precisely the number of relative cycles that this replicated manifold has. And then I have again 1 over mu r to the d minus p minus 2 times this vector, some matrix that is n by n minus 1 by n minus 1 times this. And it just so happens that this matrix is obtained by solving a Laplacian equation on this funny manifold that I had. And it happens that this matrix goes to plus infinity, diverges. All its entries are plus infinity, precisely when d is less than or equal to p plus 2. Which means that in these cases, only the n equals 0, the vector n equals 0 term contributes here. And you get 0 for the entanglement asymmetry. So again, you have a plot. So all in all, what you have to keep in mind here, that this is log of some function of r, mu r, that is 0 if d is smaller than or equal to p plus 2, and goes like the same behavior as before, log mu r to 1/2 in the other case. And not only that, this function is monotonic. So you can show that, yeah, for various values of p, when symmetry breaking is allowed, it goes like this, like the function before. So basically, because I'm out of time almost completely, the upshot is that even if I'm given access only to a subregion of my theory, I can compute the entanglement asymmetry. Now it's properly entanglement. I can compute the entanglement asymmetry for that subregion, for the states that I chose. So sorry, the boundary conditions here are chosen such that the states are roughly the same as the previous ones, are maximal symmetry breaking. And then I get 0 asymmetry when the dimension of space-time is smaller than or equal to the critical dimension, and something non-zero that is monotonic when symmetry breaking is allowed. And yeah, it approaches here it approaches the behavior that the entanglement asymmetry with no subregion had. So yeah, that's more or less what I had to say. Yeah, thank you. Yeah. Sure.
Symmetry. So I think there should be a relation with this.
That may well be true. I don't have a comment. Yeah. I think good. I think something similar was either conjectured or proven or commented in a recent paper by Yifan Wang and collaborators. for non-invertible symmetries, which if they manage for non-invertible symmetries, I suppose it's true also for invertible. But they were in 1+1D. So I think what you say may be indeed correct, and it's very interesting. Thanks. Yeah.
I understood this is like a sum over symmetry resolved.
In some sense, yeah.
Can you say anything about the individual? They all each one be monotonic? Or is it only
This is a good question. I don't really know, because you in this case you have to first take the sum and then consider the entanglement entropy, which do not obviously commute with one another. But it's a good question to keep in mind if you perhaps want to compare the symmetry resolved ones. Maybe that's a good question to ask. Yes, it changes slightly, so the slopes change slightly, but the asymptotics are the same. Yes. Can I? Well, I need to know the precise form of this matrix. In some cases I can. Why? Why?
Can you take the
In some cases, yes, I think. Yes. N minus 1 is the size of the matrix. Essentially, this. All right. I need to know the eigenvalues of the matrix. If I know the eigenvalues of the matrix, I can't. Yes, exactly. Not in this form, but once I have. Yeah, maybe you're right. Maybe so I can take it at the limit for sure. Here I can take it because here it depends only on the determinant of the matrix. But to actually capture this behavior, you're right that I can't. But I can, right, so what I can do is I can plot it. I can extrapolate, or in fact my Eduardo can extrapolate from the plots for various n's to what is the plot at n = 1. This was done sometime. Yes.
assuming that it's a rational value?
Yes. This was done also by Agon, Jaferis, Hedrick, and Casco a few years ago for calculating their. We gained that we don't. So first of all, that the non-compact pieces that they had cancel, the ones that depend on the cutoff cancel between the two, and secondly that yeah, we take a difference between the symmetrized version and their computation. Okay, we also extend it to p-form symmetries, but okay. And yeah, basically we build upon their calculation. We're using their calculation. Not really, no, because yeah, but there's a difference of entropies that gives a contribution. Right? There were two curves, which we subtract to take this one if you want. They only had one curve. We make the other one, subtract the two, and make this one. Does it? I don't remember. Did they plot the curves? I don't know. Yeah. What are the properties? I think this is, since this is a path integral computation, it basically just boils down to, yeah, there's no, I don't know of properties of a theory that can always allow to take the limit. In some cases, for instance, in the previous case that I had this temperature controlling my parameters, my states, I could take the limit of the temperature going to 0 first and the replica index to go to 1 after. In that case, I can do it.